Well, welcome everyone. We are thrilled to have you here with us today. My name is Mary Beth Gassman, and I am a professor at Rutgers Graduate School of Education, and I also serve as Associate Dean for Research. One of our new initiatives is our faculty research series, which we are hosting throughout the year. We will feature our amazing faculty doing wonderful presentations related to their research. So we are thrilled to have you here with us today. This event is, of course, sponsored by the Rutgers Graduate School of Education, and we hope that you will follow us on Twitter and Facebook and LinkedIn, Instagram, wherever you would like to follow us to learn more about all of the events that we have at Rutgers GSE. I want to introduce the event for today, which is called Preparing Students for an Ever-Changing World, the Investigative Science Learning Environment, which is ISLE approach. And I'm thrilled to have with us today Dr. Robert Zisk, who is an assistant teaching professor and coordinator of the Physics and Physical Science Education program at Rutgers Graduate School of Education. His work focuses on developing teachers and understanding how teachers develop the knowledge needed to teach physics and science effectively to help their students think like scientists. Dr. Zisk also works with in-service teachers and has led over 100 workshops and professional development sessions for teachers all across the world. So, Rob, I am thrilled to have you with us today. And Rob is going to do a presentation for about 40 minutes, and then we are going to take questions. You can enter your questions in the Q&A on the webinar. We would love to have questions from you, so please do that at any time, and we'll have a Q&A period after Rob's talk. Welcome, Rob.
Thank you, Mary Beth. I'm happy to be here and to be able to share the work that we're doing in the Physics and Physical Science Education program. As Mary Beth said, today I'm going to be talking about the investigative science learning environment approach and how we use it to both teach our students and train teachers. So as I said, today we're going to be talking about the investigative science learning environment, which I will call ISLE throughout the program. In the talk, I'm first going to say, what do our students need to know? What our students need to know in 2023 is much different than what students need to know many years ago. Then I'm going to be talking about the investigative science learning environment approach and how we use it to train students and teachers. Then I will talk about how we prepare teachers to help our students develop the necessary skills needed to teach students using the investigative science learning environment approach. And finally, I'm going to talk briefly about how we train our teachers at the Graduate School of Education. So what do our students need to know? Whenever people ask me what I do and I say I work with physics teachers, they have a very stereotypical idea of what physics is. It's a bunch of numbers, math, equations. And if you think about a typical physics class, most people think that physics are typical problems like this. How long does it take a rock to hit the ground if it's dropped from 12 meters? What is its velocity right before it hits the ground, right? A simple problem with acceleration and velocity. Or what is the net force exerted on a 115 kilogram cart traveling at 30 meters per second that comes to a stop in 13 seconds? Or what's the current in the circuit is 500 milliamps. What's the potential difference of a battery? The potential difference in the battery is 1.5 volts. What is the resistance of the light bulb in the circuit? These are all typical physics problems that you might see in a physics class and things that you might remember from high school or college when you took physics. For years, this is what we expected our students to do. But today, if I give one of my students these problems, all they need to do is go online and go into some AI, just like I did, and ask ChatGPT, what's the acceleration of an object traveling at 30 meters per second that stops in 6 seconds? And in 15 seconds, which was actually seemed to take a long time, ChatGPT was able to spit out an answer. It said the formula needs to be used. It says what the variables are. It says what values to plug in and how to calculate the acceleration. Solving physics problems is just an application of a correct algorithm and equations. The question is, though, what do our students need to know now? Do they need just to know how to solve problems, or do they need to know many other things? There was a publication in 2018 called The Future of Education and Skills, Education 2030. And it was put out by the Organization for Economic Cooperation and Development. And they discussed what our students need to know as we move towards the future. One of the things they pointed out was, as trends such as globalization and advances in artificial intelligence, such as ChatGPT, change, the demands of the labor market and the skills needed for workers to succeed, people need to rely even more on their uniquely human capacity for creativity, responsibility, and the ability to learn throughout their life. So they need to learn how to learn new things, how to process information, how to analyze information, how to take what they've learned and use it for something new. Social and emotional skills such as empathy, self-awareness, respect for others, and the ability to communicate are becoming essential as classrooms and workplaces become more ethnically, culturally, and linguistically diverse. Achievement at school also depends on a number of social and emotional skills such as perseverance, efficacy, responsibility, and curiosity. The interesting thing here is there's nothing about solving physics problems. Now, I'm not saying physics problems aren't important, but these are not the essential skills that our students need to succeed in the classroom and in the world. The publication went on to say that disciplinary knowledge will continue to be important, but more importantly, epistemic knowledge, or the knowledge about the disciplines, such as knowing how to think like a mathematician, think like a historian, think like a scientist, that will be significant. And that's what enables the students to extend their disciplinary knowledge. By thinking like someone in the discipline, you can then use that to learn new things and create knowledge on your own. It's much more than just procedural knowledge, which is also important in the discipline. So in summary, what do our students need to know and be able to do? Epistemic knowledge is important, so knowledge of the discipline, how knowledge is created within the discipline. Creativity, communication, collaboration, being able to work together, being able to communicate. These are all very important things that sometimes we don't see in classrooms, but thankfully we're seeing more and more. Perseverance, being able to persevere while problem solving, being able to figure out different problems, being able to try things and try again until you get it right. Learning how to learn. And problem solving as opposed to solving problems. So knowing how to be presented with a set of parameters and solve a problem as opposed to just applying an algorithm and solving a problem that you've seen before. And finally, we also want our students to think like a scientist or think like a disciplinarian. So our students need to know how to do things like formulate a problem. If you look at a phenomenon, what problem is actually there? They need to know how to collect and analyze data. They need to be able to identify patterns in their data. They need to be able to test ideas. They need to be able to evaluate assumptions and solutions. Is the conclusion correct? They need to be able to distinguish evidence from inference. So are you making inference, or is there actually evidence that says that this is correct or this is the correct way to think? And finally, how to argue scientifically. These last two are something that I've noticed more and more that in our classrooms that are becoming more and more important. Every day, students are exposed to inferences or arguing without evidence. We want our students to see that when you're making a claim, you need to have evidence. You can't just say, this is how I feel, or this is what I believe. If you can back it up with evidence, you have a much stronger case. And similarly, how to argue scientifically. If you're creating an argument, you need to have the evidence to back it up. You can't just put something out there in the world and hopefully it sticks. You need to make sure that what you say is actually backed up by evidence. And conversely, when you're evaluating the millions of pieces of information that are thrown at you every day from Twitter and all in social media and TV, you need to be able to say, what is the evidence behind what these people are saying? Do I have to believe everything that I read? And is it okay to believe stuff if there's no evidence? And the answer, we want to make sure that students have the evidence behind what they believe. And this has been a question, how can we help our students think like scientists? Has been a question that's been investigated for quite some time, especially over the last 25 years. And the answer in most of the studies has been this idea of active learning and interactive engagement. We want students to be active members of the classroom. The teacher is just a facilitator. The students are actively creating knowledge. They're coming up with ideas. They're testing ideas. They're evaluating their own solutions. They are communicating their ideas to each other. The classroom is a collaborative space as opposed to the teacher sharing their own ideas and having the students listen and then practice those ideas. In many studies inside physics courses, active engagement and interactive engagement and active learning has shown to be more effective for student learning and student growth than more traditional teaching methods that you might think of if you think of a physics course. So today, I'm going to be talking about how we can help our students to learn to think like scientists while also helping them develop skills such as communication, collaboration, creativity, and perseverance. These things go hand in hand. We want our students to learn the content through collaboration and through creativity. We don't want them to be told the information and then for them to study it themselves and memorize it. So how do we get them to collaborate? We can just ask ChatGPT. And I actually typed into ChatGPT how to collaborate, and it gave a very thorough list of the steps to take to how to collaborate. The issue is that while ChatGPT can give us an algorithm on how to solve a problem, communicating clearly, establishing common goals, building trust, using each other's strengths, those things cannot be done on a computer. They have to be done through engaging and collaborating with others and communicating with others. So while we want our students to learn knowledge, have knowledge of the discipline, we also want them to be able to gain interpersonal skills that will help them communicate and collaborate and share ideas. So now I'm going to be talking about the investigative science learning environment. And so how we help our students to learn to think like physicists. And I say physicists here because I am a physical science and physics educator. This method can be used across content areas and actually has been used outside of the sciences as well. And the framework stays the same. It's just the content that changes. So the investigative science learning environment is a holistic interactive engagement approach to learning and teaching physics that has a goal of engaging students in physics by following the processes similar to those that physicists use while constructing and applying new knowledge. The key thing here is that we are engaging students, and it's an interactive approach, and that the students are constructing and applying new knowledge. Constructing and applying are different than this idea of memorization. The students are taking an active role in building knowledge and creating the knowledge in their minds, and then sharing it out to others. The IEL approach is an approach to teaching and learning physics that helps students that helps engage students in the practices of science based off the following assertions. First, students as scientists learn by engaging in an interplay between experiments and theory. So they are constantly moving between experiments and then using that to construct a theory and then testing that idea. And when they get to the point where they test the idea so thoroughly that they cannot disprove their idea, that is what they work with. Learning physics is a cognitive activity that entails coordinating multiple representations to construct meaning. So students in the IEL approach are reading text, they are looking at data, they are making observations of natural phenomena, they are drawing different representations, they have mathematical representations, which everybody associates with physics. They are constantly having these interplay between different representations and have consistency between those representations. The other assertion is that learning physics is also a social cultural activity. You cannot learn physics on your own. In order to effectively develop ideas, you need to interact with others in your classroom, interact with other media. By using others and sharing ideas and reading different things and analyzing data, That is how knowledge is constructed. It is not constructed on your own. And finally, learning physics should be empowering. Often, even the students in the physics and physical science education program will say to me, I never liked physics growing up. I finally was good at it in college. And if they're a chemistry major, a lot of them say, I don't like physics. It scares me. But by the end of the program, often a lot of them say they actually like physics and they want to teach it more than chemistry. Learning physics is not difficult. We don't want our students to think it's a scary or unobtainable thing. We want students to celebrate the construction of knowledge and celebrate their successes while they're learning physics so that they are empowered and can show that they are able to learn and succeed in a discipline that is traditionally seen as more difficult. So this is the IEL approach. And this is what we call, and my students call the IEL cycle. I like to give this example whenever I start my courses. And I say, if you're driving down the road to work and you have to be at work by 11 o'clock and you see a bunch of headlights in front of you, after getting really frustrated that you're going to be late, possibly be late, you start doing things like looking out the window to see if you can see flashing lights or checking your phone to see if Google Maps or Waze says that there is an accident ahead. Then the next thing, so you have these different ideas, right? And then you test them. You say, is there an accident? And if there's, so you look on your Google Maps, you say, there's not an accident. Well, what else could it be? Then you say, oh, I forgot there's construction. Everything we do is a series of making observations, coming up with ideas based on our observations, and then working to try to test them. And when we test our ideas, we have a prediction in our mind of what will happen if our idea is correct. So if there's an accident up ahead and I look out the window, I should see flashing lights. If there's construction and I pull up my Google Maps, I should see the construction symbol a half mile up the road. Everything we do throughout life is just a cycle of observations, coming up with ideas, and then testing those ideas. And if our prediction matches the outcome of our testing experiment, then we say, our idea was probably the most plausible one. But if it doesn't, then we move on to another idea. This cycle is what our students do throughout their coursework in physics and also in their pre-service teacher program. Every learning cycle starts with observation of phenomena. Then once they do that, they look at the different phenomena, they identify patterns, and they say, what are the explanations, the models, the hypotheses that I can come up with to explain the observations and explain the patterns? Then once they do that, they say, look, I have this really long list of possible ideas and possible explanations, but we don't want a whole list because we're human and we want the right answer. Not that we can always get to the right answer, but we want to narrow down our list to the most plausible idea. So then we come up with testing experiments to test their ideas. And we always have a prediction for each testing experiment. If my model is correct, what should happen in this experiment? And then we evaluate the outcome. Does the outcome match my prediction? No, then we get to cross that thing off our list and move on to the next one. But yes, but if the prediction does match the outcome, then we can try more testing experiments until we cannot rule out this explanation that we have. This cycle is seen over and over again throughout the student's learning process. And this is how they're able to construct their own ideas. Throughout the learning process, students are working in small groups. They create a learning community. This is very important because I might make an observation, and when I make that observation, I might not see the exact same thing as someone else. I might not make the exact observation that someone else did. By working in small groups, we can create a much larger list of possible ideas. We can create a much larger list of possible testing experiments. We can find different patterns in the data. We can share ideas. This also makes learning lower stakes. If you're in a group and you're sharing ideas, you are not the one that's on the spot. the whole group is on the spot and you have the protection of that group. So when you succeed, you can all share in your successes. And when you might not do the best you can, or might not, the outcomes might not be what you expected, you are not the one that got it wrong. Your group just needs to go back to the drawing board and figure it out again. The other thing that we have embedded throughout our approach is opportunities to improve work with no punishment. We see learning as a continuous cycle. If you don't get it today, you might get it tomorrow. And if you don't get it the next day, you might get it the day after that. So you are continuing to improve and you're continuing to learn, and you are able to persevere while you are creating the knowledge that you need to create. So I always like to give a quick example of the IL cycle. And this is one of the first ones that our students do in the classroom. Imagine you walk into a room and it's completely dark and you turn on a light. This is a phenomena that students experience every day. It might not look as industrial as this, but when you turn on a light, what happens? The entire room lights up, or at least a large portion of the room. Even though the light bulb is small or in a corner, you notice that much of the room lights up and it's much less dark than it was before. So we do the same thing in the classroom. The students walk into the classroom, we turn the lights off, and then we turn the lights on, or we turn a light on in the middle of the classroom, and we ask them, what did you see? And what all students will say is the light appears to go in all directions from the light bulb. They might not use those words, but students will say, well, the whole room lights up, or the light lit up over there, but it's bright over here as well. The good thing and the important thing about making observations is every student can make an observation. All students are able to tell us what they see or what they hear or what they notice. This is not a high stakes question at all. This allows students to be successful right from the bat on in these cycles before things might get a little more difficult. So then in the cycle, once we make this observation, the next thing we have to do is, if we're trying to answer the question, how is light emitted from the light bulb, we need to come up with a hypothesis. What is it about the light bulb, how light is emitted from the light bulb, that enables it to light up the whole room? And a possible hypothesis that every group of students will come up with says that we'll draw a picture much like this, which is a light bulb with beams coming out of it. And they'll say that there are individual points in the bulb, and at each point, a single ray of light is emitted. And this idea comes from every time they've seen a cartoon light bulb. If someone has an idea, like in a cartoon, and there's a light bulb over their head and the light bulb goes on, they see rays of light shooting out of it, just like this. So now we have this idea. Maybe light is emitted from each point individually on the light bulb, so let's test it. And so they talk in their groups, and inevitably at some point, one of the students will say, we can test this by seeing if a beam of light comes out of one point on the light bulb. And then they say, well, how are we going to do this? And then one of my students will always put their hand over the light bulb, and they'll find out really quick the light bulb is warm and they shouldn't do that. I've learned now to tell them before to not touch the light bulbs. So the students will get a piece of foil, or they will get a large piece of cardboard, and they will poke a hole in the foil of the cardboard and cover the bulb. And they will isolate one point on the bulb, and then they will shine it on the wall. And their prediction is, if each point on the light bulb emits one beam, then what should happen is we should see a small round dot on the wall, much like if you shined a laser pointer at a screen. And so the next thing is we actually have to test their idea. And what they actually find out is that the spot on the wall is much bigger than the spot on the light bulb emitting light. So in this case, the outcome does not match the prediction. And then they can disprove that each point in the light bulb emits one ray. So now we have to go back to the drawing board. Our only hypothesis was disproven, so what are we going to do next? We have to make another hypothesis. So inevitably, after a few minutes, students of all ages, at least from middle school on, will come up with some kind of model that looks like this. Maybe the ray gets bigger as it comes out of the light bulb. Maybe there's multiple rays out of the light bulb. So they revise their model, and what eventually we get them to is this idea that an infinite number of rays are emitted from each point. So that light is emitted in all directions from that single point, just like light is emitted in all directions from the light bulb. Now, this is much cleaner than what would actually happen in the classroom. This involves students talking and working, and the teacher moving around to each group and facilitating and asking questions. But now we have our new model, and what do we have to do again? We have to test it. And one of the testing experiments that a group of middle schoolers came up with last year was that you need to hold some sort of object in front of the light to produce a shadow. And so if each point emits an infinite number of rays, as the object moves away from the light and towards the wall, the size of the shadow should approach the size of the object because fewer and fewer of the beams are getting blocked. And they do the experiment. They did it with a flashlight. And what they notice is that's exactly what happens. The flashlight beam spreads out. As you get closer to the wall, the shadow gets smaller. As you get farther away from the wall, the shadow gets larger because it's blocking out more and more of the rays. And this supports their idea that each point on the bulb emits rays in infinite number of rays in all directions. So at this point, we then support our hypothesis, and then we can use it to apply to new ideas. And if I was giving a longer talk just on the Isle approach, just on this, I would talk about the different application experiments. But students come up with different things like figuring out how a camera works and why the image on the lens of a camera is actually upside down. They then apply their model to new ideas, and hopefully the model holds up. So this was content, right? They learned how light is emitted from an object. But I also mentioned that we need things like creativity and collaboration and perseverance. Creativity is everywhere throughout the Isle approach. Under the Isle approach, students are tasked with producing multiple explanations for observed phenomena. They have to come up with these ideas on their own. They are sometimes crazy ideas. In fact, in my classroom, I don't say come up with explanations or hypotheses. I say come up with as many crazy ideas as you can list. And trust me, some of them are out there, but we work to try to test them if they are testable. Students are then tasked with designing experiments. Again, they're being creative here. They have to test there is no one right experiment. I have experiments in mind when I come into the classroom and if I'm designing my lessons, but there's no one way to do these testing experiments. And then they have to work together and determine how to collect and analyze and present and communicate the data and results. So throughout this process, they are constantly being creative and they're problem solving. There is a cycle that they follow. They know that they go observation, hypothesis, testing, experiment, prediction together, and then evaluating results. But every problem is different. Every phenomenon they observe is different. There is no one way to solve each problem. So throughout this process, they're being creative. They're learning to think. And then collaboration and communication. And these are the pictures I'm going to show you in the next two slides are pictures from colleges and high schools throughout the country. What you'll notice when you walk into a classroom that uses the Isle approach is that the students are the ones in front of the classroom. The students are the ones working together. The students are the ones that are responsible for the knowledge and the creation of knowledge. So in the top left, you see students actually trying to figure out what the speed of a ball is before it hits the ground and test that idea, much like a traditional physics problem that I mentioned in the beginning of the talk. Then in the other picture across from it, there are students working on a whiteboard. They are trying to figure out an inclined plane problem. And at the bottom, there is a student drawing a solution on the board while the other students are working together and sharing their ideas. You can see in this picture, every student is watching what the person at the board is doing. That is not the teacher, it's another student. And you can see some of them pointing, Collaboration is spread throughout this approach. No one person is responsible for their own learning. And these are high school students from a school in New Jersey. And you can see them working together. You can see the group in the middle. They are working on a mystery circuit board with light bulbs. They're screwing the light bulbs in. And you can see the two on the sides. They're actually doing the same exact activity. They're doing an activity called Where Does the Cars Meet? And students are working together to take data. They're designing their experiments. There's a student on top of a lab table, trying to track the motion of the car using a video. So again, in each of these cases, they're working together. And also then in the middle, you see a whiteboard. And if you look actually on all the pictures, for the most part, there is some sort of whiteboard. And this is where the students share their ideas and communicate their ideas. This is how they share it with the class. And in this case, you can see that students have a prediction, they have a procedure, they have the data that they collect, they calculate uncertainty, and then they come to a conclusion. They are following the IL cycle right on this whiteboard. They're communicating, they're sharing ideas, they're working together to come up with their own, to create their own knowledge. Now, this approach is much different than what many students experience in their classrooms prior to when they come into a classroom that's IL-based. And there might be some pushback initially, but by the end of the course, students are generally very positive with what they say. One of the teachers that I will talk about shortly did a dissertation on students and how they progress through IL in their course. And she had to pull some quotes from what her students said throughout the years. And these are some of the things students said. I don't really think it was about the grades. I think my motivation is always understanding. Like, I aspire to fully understand what's going on. And that drives me to ask questions, to think about answers, to go over tests, and to practice more until I get it right. Of course, the students are still talking about taking tests and practicing. But here you can see the student is motivated by understanding. They're not just motivated by getting the answer right. They want to know the answer. They express motivation throughout their statement. Another student said, I feel like I finally understand what it means to have an active role in an investigative environment. So they're not just sitting passively anymore. They're actually actively involved. A lot of it stems from the need for more effort to inquire and to figure out things that you didn't understand in order to be helpful. This idea is order to be helpful is that students want to work, once they're in groups and they learn that they all have to create knowledge together, they are motivated to help each other and to learn things so that they can all succeed. They're no longer just learning for themselves. They're no longer creating knowledge just for themselves, but they're creating knowledge as a classroom. And finally, I really like this quote. I learned a lot about physics and a lot about myself. I realized that I'm capable of a lot more than I think I am. And for many students, when they walk into a physics class, they are scared. But usually hopefully by the end of our course, by the end of the physics course, they feel much more successful than they did walking in, and they learn much more about themselves. And these are the quotes that we like to see. They're motivated for understanding. They want to be helpful within their group and their collaborative environment, and that they realize they can actually do it and succeed. So the final thing I'm going to talk about is how we prepare teachers to help students think like physicists. And this is not much different than how we prepare students to think like physicists. So how do we prepare teachers to help our students learn? Lecturing does not work. I cannot lecture to my students and tell them this is how you have to be a good teacher. This method, just like thinking like a physicist and creating knowledge, in order to become a teacher that can employ this method in the classroom, become a teacher that can do anything, students need to be actively learning throughout the process. So our pre-service teachers, our students must first experience learning in the IL environment that helps them to think like physicists before they can actually help their students think this way. So how do we develop this knowledge and skills needed to teach? We help them develop these skills through apprenticeship. And we use the cognitive apprenticeship model throughout our program. So first, they start with context set model proficiency. So they walk into our classrooms, and when they're in their pre-service teacher classes, they are experiencing the same type of instruction that we expect them to use throughout their experience. Then there has to be provided scaffolding and coaching. So there are times where students get feedback, and I'll explain more about that. And there's less and less feedback throughout. And then again, we need to slowly remove that feedback. And then finally, they need to have a chance for independent practice. And that, in this case, and in teacher education, independent practice is the student teaching internship. Embedded throughout this process is reflection. So the students are constantly being asked, what did you see? What did you do? How did you collect? How did you construct that idea? Then what type of questions did I ask? Or when they're teaching, we might give them feedback that says, John over there asked this question. Did you hear that? And if you did hear that while you're teaching, let's go back and say, how can we address that question? Then we ask them to evaluate their teaching. And then finally, we ask them to say, now you evaluated teaching, what are you going to do next time? So throughout each of these steps, there's a constant cycle of reflection. So for the rest of the talk now, I'm going to talk about our teacher preparation program. And our physics teacher preparation program was founded by Eugenia Etkina in the early 2000s. It's about 20 years old now. We are consistently one of the largest producers of physics teachers in the United States. And we have a large community of graduates who continue to learn and support each other after graduating from the program. I believe the community is now between 170 and 190 teachers. Many of them I have met, even if I never worked with them, and many of them continue to come back and work at Rutgers or work with us or just come to our weekly meetings, which I will talk about at the end. And one of the things we're most proud of is that 2 of the last 4 National Physics Teachers of the Year were graduates of the program. Matt Blackman is in the middle, and Danielle Bouget is on the side, and she is wearing a dress that has physics equations all over it. Both of these teachers have graduated from our program about 14 years ago. And they both won Physics Teacher of the Year, and they also both teach in our program. So they are active members of our community, and they're helping to train new physics teachers throughout. The structure of our program breaks down like this. So there are really 3 parts. First, there are physics teaching methods courses with the same theoretical framework, including micro teaching experiences. So throughout all of their methods courses, they are using the ISLE framework. They are experiencing lessons in the ISLE framework. They are designing lessons using the ISLE framework. They are teaching lessons using the ISLE framework. Everything they do is based around that framework. They also have micro teaching experiences, and micro teaching is what we like to call flight simulator for a physics teacher or flight simulator for a teacher. They are teaching in front of their peers, and they get immediate feedback from their instructor. Oftentimes they're asked to stop and reflect on what they just did, or stop and rewind and change what they said. But this is one of the times where, as a teacher, they get immediate feedback. It's almost as good as having an earpiece in their ear while they're teaching in front of the classroom. They also have a series of clinical experiences. Our students at Rutgers have 3 clinical experiences in the classroom, and then 1 community-based clinical experience. But all of their classroom-based clinical experiences are done under the supervision of teachers who went through the program. So we have teachers ranging from those who graduated 4 years ago to those graduating 15 years ago that frequently and are very willing to take on our student teachers and help train them. And finally, we have a vibrant online and in-person community that supports new teachers and reinvigorates the experience. I will talk about this more, but I will say that last Friday night, a group of 20 of our graduates got together to learn physics and talk about how they teach physics in their classroom. And this is actually a monthly and sometimes twice monthly meeting, along with an online community and a Discord community now where they share their own ideas. So I mentioned previously that learning how to teach, we use a cognitive apprenticeship model. And so I want to briefly talk about our model here. So the first thing they do is experience the learning in the ISLE environment. So this is the sheltered learning in the same context that they'd be teaching in. And you can see in these pictures, these are students in the first semester of the course. These students have been teaching for quite a while and have their own student teachers. But you can see that they are engaging the same activities that you saw previously what the students were doing. And actually the picture in the bottom right, they're actually doing the exact same activity that the high school students were doing. The picture is on a few slides ago. Then they also act as a teacher in multiple methods courses. So they are doing their micro teaching. In each methods course, they are teaching a full 3-hour lesson where they get scaffolding and feedback right away. Then they have a more sheltered teaching experience. So our physics teachers actually teach in a lab at Rutgers University and a recitation that uses the IEL framework. And often teaching in a college classroom is much easier, at least classroom management wise, than teaching in a high school classroom. This is a sheltered environment where there's still some scaffolding, but not as much. They have the help of the person who coordinates the course, who is always there leading lab meetings and providing feedback. So this is the sheltered teaching. They get more experience teaching in the IEL-based course. And then finally, they actually work as a high school or middle school student teacher, and they are placed with graduates of the program. So even here, while they are doing independent practice and the scaffolding is removed, the person that is mentoring them uses the same exact framework in their classroom. So at each step of the way, they are experiencing and teaching using the methods that we expect them to. And the other thing that's embedded with this is they are never on their own. When we talk about communication and collaboration, they have their cohort, so the students that are in the program with them, to work with throughout. They're learning with them, they're sharing ideas. Then when they're lab and recitation, they have the other lab and recitation instructors and the course instructor that they work with. And then finally, when they're student teaching, they are collaborating with a graduate of the program. And a lot of times, many graduates of the program, because our teachers tend to teach in the same schools. So they have this community that they work with. So they are developing this collaboration skills throughout, the same type of skills that we want our students, their students, to develop in the high school classroom. The other thing I want to mention, because I put it about 20 times in the last 3 slides, this idea of how we embed reflection throughout the learning process. Students need to know what they did and why they did it. I always tell my students that, I always ask my students at the end of the class, what did we learn today? And after a while, they get annoyed at it. They like doing it, but they get annoyed because they know the question is coming. And one student said, why do we always do this? And I said, it's important to reflect on what you know, what you learned. What did you learn? What was the process? And how did you do it? The key thing here is how did you do it? And then how are you going to apply it to something new? And that's what we ask throughout the process. So as I said, pre-service teachers learn to teach by experiencing the same instruction they employ in the classroom. As they learn through the IEL approach, they reflect after each learning cycle. They talk about content. So first they say, what idea did we just invent? So the students always love in like the 3rd class of the program when they actually invent Newton's laws. And they kind of know that they do it. And then when I take what they write down on what they've written down on their whiteboards, and I show them what Newton originally wrote, they see that they actually invented Newton's laws. And they all know them when they walk into the classroom. At least they have an idea of them. But then by the end, they realize that they were able to invent Newton's laws without me telling them. So what did we just invent? What elements of the IEL cycle did we use? Did we make observations? Did we test their ideas? What representations did we use? What difficulties students might have? We also asked them, what questions did I ask them to help them learn? What questions would they ask? So we're constantly asking them to reflect on the learning process. We carry this habit, all of them, we try to get them carry this habit throughout their teaching internship and into their careers. And even when they have these community meetings, we do reflect on their experiences, reflect on their teaching. We help them to be able to analyze their own teaching and their students' learning in order to help their students learn. One of the most essential and unique parts of our program is our community of learners and our community of graduates. This community is built even before they start in the program. The summer before they start in the program, our students meet, they work on physics together, they work on their physics knowledge together. They meet and work to learn how to teach in the course that they're going to teach in. So even before day one, they're building a community with each other. Then within their coursework, they're constantly working in groups. They are never on their own. There's very little time where they're working by themselves. Then they do a big project in each course, which is their micro teaching, so they work together. And then finally, during clinical practice, they're constantly communicating. All of my students communicate with each other. They help each other. They really are assets to each other throughout the program. And then once they graduate, they don't go away. All of my students still talk to each other. They have a Discord community. And this is a picture. It's a chopped picture because it didn't capture everybody in one. But this is a picture of one of our community meetings. Students are meeting around a table. They're discussing ideas. These are teachers who graduated anywhere from 15 years ago to, in this picture, 2 years before. Graduates throughout the program meet with each other and work with each other and share ideas. No one is alone in this program. They use each other as an asset. They use each other to share ideas, to learn new things. They also use each other as a sounding board because sometimes teaching is not easy. But all of these things helps our teachers succeed and help them to be happy in their profession. And I'm happy to say that our program is quite successful. Since 2003, we've graduated over 170 physics teachers. The average American university graduates about 1 physics teacher a year. So we have graduated much more than that. Our overall 5-year retention rate is about 90%, which is much higher than the overall 5-year retention rate among teachers throughout the country. And I want to talk about the people who left because we also know them as well. They're still part of our community. So 5 graduates quit teaching completely or did not start. Several others went to grad school to get their physics PhDs. 2 of them got their PhDs in physics education. 1 went to law school after 6 years of teaching. 2 people now work for NASA. 1 works for the Jet Propulsion Laboratory. And 1 is actually a designer for physics simulations in Colorado for PhET. Our teachers are very successful. They have high observation scores. They have high scores on tests of content knowledge for teaching. They have high student scores on AP exams. They have high rates of transfer. And I don't mean transfer like leaving the classroom. I mean transfer by students learning skills in one context and being able to transfer in the new context. Those quotes you can also that I put previously can point to successes of our teachers in teaching their students to feel successful. And like I mentioned before, since 2019, 2 of our graduates became National Physics Teachers of the Year. So in summary, how do we help our students think like physicists? Students need to know more than disciplinary knowledge. They need to learn to think like scientists and physicists and learn the skills needed to thrive in the 21st century. Things like communication, collaboration, learning how to learn, perseverance. These are all very important things. The IEL approach engages students in practices that enable them to develop knowledge and skills, to learn to think like physicists, to collaborate, to communicate, and think creatively. And finally, to prepare teachers who help their students to think like physicists, teachers need to experience learning that helps them to think like physicists and then practice designing and implementing instruction that does the same. They cannot just learn this through lecture. They have to experience this instruction to be able to do it in the classroom. Thank you.
Thank you. Thank you so much, Rob. I'm going to ask you to take your slides down so that we can have a conversation. We've got a bunch of questions that have come in, but thank you so much. I want to say that as someone who took physics when I was in high school, and it was taught in a way that was not collaborative and not engaging, I really love seeing what you're doing and what you're talking about. And I just really enjoyed listening to just, the model of how to do this and how to do it well. So here's some questions. I hope you're all ready to answer them.
Thank you.
Here's a question which I just love. Do you think that an approach like this can be replicated for other disciplines other than physics or STEM, and has it been?
Yes. Within the sciences, this is where I'll start. There are people that have done it in biology. There are also people that have done it in chemistry. We actually have a whole group of researchers that are working on ionizing chemistry, but that's within STEM. This has been used in history classes and social studies classrooms. And while the discipline of history is not exactly the same, the idea of looking at something that happened in history and then looking at different pieces of evidence and then coming up with an idea for why this happened or what led to this is very similar to this process. Similarly, well, I will talk about that more. And this is something that I've actually talked to in the past, I've actually worked with elementary teachers, and when they're planning lessons in social studies, I've actually had them say to me, like, I've used this approach, the same thing I learned in your science methods course, and it works really well. This approach works in any discipline as long as you realize that there are differences between them and you adapt it slightly to fit what that discipline is. There is even a researcher who works in special education that has used this model in her teaching as well.
Oh, thank you. Yeah, it reminded me a little bit of something that I saw at Xavier University in New Orleans that they use in biology, where they're trying to really foster a collaborative learning environment over a competitive learning environment. And it reminded me a lot of that. And in fact, one thing I wanted to ask is, this is one of the questions, but I'm also curious about it, which is, do you think that this helps students to be less kind of competitive or cutthroat in the sciences and fosters more collaboration, more support of each other? And I wonder, because I know that that can be really empowering for women and also students of color. I wonder if you have any thoughts on that, because I kept thinking about that, and one of our listeners as well.
Yeah, this is something we've actually talked about frequently. It creates a low stakes environment. We never ask the students for the right answer. And I think right off the bat, that makes it a low stakes environment for everyone. And the other thing I didn't talk about in this talk, I've talked about it previously, is one of the scariest parts of people about physics is math. And math ends up making it competitive, because if you don't know the math, you're not going to succeed. And those that do know the math are going to succeed, and those are going to be the ones seen as most successful in the classroom. So that's not introduced till later, till after the students start developing their ideas. But I do see that it does create an environment that's less competitive. Every student is willing to share their ideas. We encourage that. We never put anyone on the spot. Sometimes there's, when you're talking especially about of women in the classroom, there is some intentional ways we make the groups to encourage them to participate. But this idea that they're participating in groups and that everybody's voice must be heard is really important. The other thing that we do, and it was on the whiteboard to encourage participation, is we expect everybody to participate. So everybody gets a different color marker. And this is something really simple, but we expect everybody to have some contribution to the whiteboard. Or when they were doing work online, we could go in the Google history and see that everybody participated. And if everybody's voice is not heard, then we expect them to be at some point. This has been done in many. The quotes that I sent from that were from one of the most competitive high schools in the state of New Jersey. It was ranked in the top. It's always ranked in the top 5. And when I walk into those classrooms, the students are always sharing ideas. They're never really being competitive with each other. They might be competitive outside the classroom, but in that classroom, everybody's ideas are heard. And that's some credit to the teacher, but it's also credit to the model as well, because you cannot succeed on your own. You have to have multiple ideas, and you have to work together.
Oh, I love that. I love the idea of giving everyone a different color marker. That's such a great idea. And then I just also love the whole premise of, the best science is collaborative and has people working together and lots of different ideas. And so thank you. Okay, so some more questions. One is from Timothy, who's with us, who says, I do abbreviated versions of this simply due to funding. I have a very low budget, less than 1,000 for my entire science department, for which I am the head. Where can I get ESOL? Is it ESOL? Is that how you say it?
IEL.
Okay, sorry. IEL resources that are more virtual. Any ideas?
Yes, so there's tons. We use PhET a lot, the Colorado simulations, we use them throughout. We also have a very large library of video experiments that were originally used for a textbook, but now they are freely available. We have a whole IEL YouTube channel that one of our original doctoral students in the program has created, and they are up-to-date videos. The idea for IEL is that whenever I go into a school, they ask me about funding and I say, I want to make this as inexpensive as possible. That we very rarely use very advanced equipment. And if we do, we have a video for it. Everything for IEL is basically freely available, and I can share those resources when we send out information from the webinar.
Oh, that would be great. That would be great. Thank you for that. I love to hear about free resources, and I know that videos and YouTube posted freely on YouTube can be just so helpful to scientists. So thank you. Here's another question. This is also from Timothy. What about grading? We have to grade. If we don't, they have no grades that are appropriate and they can't get into Rutgers. How do you suggest a fair, appropriate manner for grading their work? That's a great question too.
So within IEL, we grade on scientific abilities. So we have a series of rubrics that measure students' ability to engage in these scientific abilities. Again, these are freely available. And the key to this is that students are always able to resubmit. So when they're doing a lab, they submit the lab, and sometimes they self-score themselves, and then the teacher scores them, or the teacher just gives them a score. And they know that they got a 2 out of 4 on rubric 3B, which is a testing experiment rubric, but that doesn't matter. And then they have to go back and they can look exactly based on the rubric why they got the score that they did, and then they're able to resubmit. That being said, we understand that within the high school classroom, more traditional assessments need to be given, just as a requirement of the school or just the culture of the school. So our teachers do give traditional assessments, and they are often graded within, they are graded within the policies of the school. Content is not gone. It's just that we spend more time with the students developing the content as opposed to just practicing the algorithms and the equations over and over again.
Thank you. Thank you. Great answer. So another question is, so how do students in schools and also teacher candidates adapt to this kind of instruction, and how long does it take them to? Because this might be very out of the norm for some folks. So how do they do that, and how long?
This is out of the norm. And this is a conversation I have with new teachers all the time, and even more experienced teachers come up to me and talk about this. And it takes at least until November or December in a high school classroom, possibly until January, where the students really start to get into it. And it requires work. It requires a constant reflection. It requires you constantly to make sure they're doing each step. Even within our teacher ed courses, students who have a lot of physics knowledge, it takes them a good part of the semester, because we're not taught to think this way in schools. The good thing about it is that we do think this way outside of schools often. And so we try to map these thought processes onto what you do every day. The collaboration is also difficult, because in college and high schools, you're not taught to collaborate because it's what your grade that matters. So we had to change that mentality to say, look, it's not your grade that matters. And the only way you're going to be successful is if everybody in here works together.
Thank you. Thank you so much. Well, we have more questions, but we are out of time. So I want to say thank you so much to Rob. Wonderful presentation. And I really love the way you answered the questions. Lots of helpful advice. Thank you so much. Thank you to our attendees and to Rutgers Graduate School of Education for sponsoring our session today. I do want you to know that we will be sending out a recording of this talk, and we'll also send you a bunch of resources as well, as Rob mentioned, and we will give you a heads up on our next webinars in our year-long research series. So thank you so much. We really appreciate having you with us today. Thanks again, Rob.
Thank you. Thank you so much. Thank you, everybody.
Take care.